Okay, good, good.
Okay, so welcome everyone to this week's ICTS String seminar. We have Hong Liu from MIT. He's going to speak about emergent times in holography. Over to you, Hong.
Okay, yeah, thanks a lot for the invitation. Right, so we'll talk about some recent work with Simon Luther, which we presented in these two papers. So one is a shorter version, and then one is a long paper. So yeah, so whenever we started thinking about say quantum gravity, so one of the first problem we face is so-called the problem of time. So in quantum mechanics, time is absolute, plays a key role in the evolution, whether you use Schrodinger picture or Heisenberg picture. But in gravity, most of the time coordinate is actually meaningless because it's just a coordinate. It can be changed by arbitrary gauge diffeomorphism transformations. So it's hard to decide which time is physical and which time is not physical. But here I say most of the time, because in some situations there's the situation is better, because in ADS, for example, there's an absolute asymptotic time, because the ADS have a time-like boundary, and all the gauge diffeomorphism, they're supposed to go to 0, say when you go to a asymptotic boundary. So there you actually don't have time representation freedom anymore. And of course, the presence of this time, which underlies the success of ADS-CFT, and which is also the reason the quantum gravity in space-times of other asymptotics appears to be much more difficult. So let's go back to the simpler situation, just in the case of ADS-CFT. Can we actually, we can ask the question, can the asymptotic time be sensibly to the interior? Yeah, because many questions we are interested in regarding quantum gravity or the geometry happens in the interiors of the space-time. So in the special case, when the box space-time is time translation invariant, and the answer is yes, because there's a, say in the sense, there's a preferred time slice. But in the general situation, say if you have a general time-dependent cases, and then the story is not clear. Okay. So here we want to look at intermediate case between these two. So the intermediate example is provided by this internal black hole in ADS, which it's well known. So from early days of ADS-CFT, is described by 2 copies of the CFT in the thermal field double state. So there's no interaction between the 2 CFTs, which I call, one of them called CFTL and one of them called CFTR, but they are in the entangled thermal field double state. So in this case, yeah, so here is the Penrose diagram for the internal black hole in ADS. And so we separate, say, from convention into RL, future and the past region. So there's 2 asymptotic boundaries. So in this case, there's time-like Killing vector outside the horizon, but there's no global time-like Killing vector for the full space-time. So in this case, in the sense we can extend the boundary time to the region outside the horizon. Okay, so the L and R region. But then this time then stops at the event horizon. Okay, and then of course this raises many mysteries from the boundary perspective. For example, say, so how do we describe the future and the past regions? Okay, intrinsically using boundary theory language. Say how do we describe Kruskal time kind of slicing of the box space-time? Also, can we understand from the boundary theory point of view the emergence? Yeah, where does the just from the boundary point of view, how the horizon emerges and associated causal structure. So I want to emphasize that this internal black hole, the causal structure associated with even the horizon, say, can be thought as the simplest context we can probe the question of the causal structure. Of course, if you look at the general ADS space-time, you can always look at the local light cone, etc. But those questions are much more, more local. So in the sense, it's more complicated. So in the sense, for internal black hole, the causal structure associated with horizon has some global flavor, and so so provides a simpler context to ask questions of emergence of the Bach causal structure from the boundary theory. And then there's also this question which many people pointed out, first discussed in depth by Aaron Wall and Marov, is that you can also imagine, even though there's no interaction between the CFTL and the CFTR, but in the Bach, you can have observers which fall through the horizon and then interact in the interior of the black hole. Yeah, so how should we understand this kind of process from the boundary perspective? Okay. So also just to sharpen the question a little bit more, so we can ask, what are the typical boundary time, boundary evolution corresponding to the Bach picture? Say, suppose in the boundary theory, we have two Hamiltonian, HR and HL. So one natural combination we can use is so-called HR minus HL. And so this is, so this annihilates, so this operator annihilates the sum of your double states. So in the sense, this operator generates isometry on the gravity side. And so the slicing corresponding evolution of this operator, and then it's given by showing this figure. So you start with t equal to 0 slice, and then you evolve like that. So alternatively, we can consider HR plus HL, and then they will lead to evolution like this. Okay. And so both on the both right and left, you go up, but still the evolution is always outside the horizon. So in both, in this case, the evolution is all outside the horizon, and in this case, it's also outside the horizon. So the time slice. So if we want to describe this kind of, say, Kruskal time, a kind of time slicing, and then there's no obvious candidates from the boundary theory to do that. So natural question is that maybe this kind of time slicing has to be emergent. Yes, I recharacterize what this emergent means. Okay. So the goals of this talk is that I will try to explain how to do the boundary constructions of Kruskal like evolutions. Okay, just how to do this kind of evolutions, and also along the way we will describe the boundary emergence of the horizon and associated causal structure. Okay. So here is a rough plan of the talk. Is that first I will just outline the main results. So just to give you a flavor what we do. And then I will go back to review a little bit entanglement structure in relativistic quantum field theory, and in particular, the structure called type III1 von Neumann algebra. And so associated with this type III1 von Neumann algebra is actually a very interesting mathematical structure called half-sided modular inclusion and translation, which will play a very important role in our discussion of emergent time. And then I will describe how to construct Kruskal time, a Kruskal-like time evolution from the boundary theory, and then I will conclude with some discussions. So do you have any questions at this time? Okay. Okay, good. Yeah, let me just proceed. So first, let me just outline the main results. So what we can do is we will show there exist certain evolution operators on the boundary, which have the following property. So we call this G to be evolution operator. So we just generate a flow of this G using the standard explanation. Yeah, standard explanation. And so this G have the following properties. First is involve both R and L degrees freedom of the CFT non-trivial way. So not just say like previously say HR plus minus HL, So this G actually involve non-trivial couplings between R and L degree freedom. Yeah. And also this G have a very important feature is that this is bounded from below. Its spectrum is bounded from below. So this qualify it as some kind of Hamiltonian, okay, give you a flavor as some kind of emergent Hamiltonian. And so, yeah, and furthermore, we can act this evolution operator, which is intrinsically constructed from the boundary theory. Suppose we act on the Bach operator, say in the right region, okay? So here our assumption is that the Bach reconstruction from in the outside horizon are given, okay? So because we can extend the boundary time easily to the outside, to the region outside the horizon, to this R and L region. So we take that part of the ADS-CFT as given. And then naturally, then any operator in the right region then can be, or in the left region can be interpreted as a CFT operator, okay? And then we can add this evolution operator on this some operator in the right region, and then we will show that it can take it inside the horizon for sufficiently large S.
Sorry, can I ask a question here?
Yeah.
So yeah, so with Kyriakos, of course, we had an answer to the same question, and in our case, this e to the ig was related to the modular operator that you would get by looking at the set of by taking the thermofield double state and acting on it with a small algebra, you would get a modular operator which would correspond roughly to this e to the minus ig. Is this going to be a different answer, or is it related to that? To the answer?
I think it's a different, because here the modular operator here for the thermofield double state, the modular operator would be the just H, right? Just HR and HL.
Yeah, in general, I mean, if you had a non-equilibrium state, then it would be something more complicated. But yeah, yeah, so it would be something. The construction that we had would be more complicated. But this is distinct from that. It's going to be a different answer.
Right. Yeah. Here we just consider the simplest case, just the thermofield double state.
Yeah.
And then corresponding modular operator will be just HR and HL. And
right.
then by themselves, they don't take you inside the horizon.
Well, there is also the J operator. So there's also the antilinear map you need to act with. And so I mean, once you or the S operator that they call in Tomita-Takesaki theory, and that will map you between the left and the right. So of course, the interior operators must always have something from the left.
Sorry, S you just means the J times delta?
Yes, exactly. So or J times delta to the half, yeah.
Right, I think J times delta, at least in this case, in this case, does not take you inside the horizon, because we know how delta acts, we know how J acts, and neither delta and J take you inside the horizon.
Yeah, by themselves they don't, but they map you from the right to the left. So if you then combine the right and the left, then you can construct. I mean, this is just a Bezoniano-Wichmann construction applied to the thermofield double, but this will be different from that, you say.
Yeah, but that does not take you intrinsically. It does not give you a time slice, which like Kruska kind of time slice. Yeah.
Okay. I can ask again after some time. Yeah, thank you. Yeah.
Right. Mm-hmm. Good. So we'll take you inside the horizon for some sufficiently large S.
Sorry, can I just one small clarification? So
yeah,
I should think of S as time. Is that right?
Sorry.
I should think of S as time, right? Or it's just any other.
Think of it as what?
Time, T.
Yeah. So this is some. Yeah, this S you should think of it as some kind of infalling time. Yeah.
Okay. Yeah. Okay. Yeah.
So in particular.
So I have a question, and it goes up to the singularity, right? I mean, it ends at the singularity. This kind of evolution. Question. Right.
Yeah, that's a good point. I will talk about singularity a little bit later, because singularity is a little bit a tricky question. I will mention about singularity at the end. Yeah.
Okay.
Mm-hmm. So in particular, we will see sharp signatures of horizon, and in particular, in the sense that we can argue this kind of operator can be used to generate the future and the past region of the black hole, starting from the knowledge of right and the L. Yeah, so our starting point is that given the ADS-CFT for the right region and the left region, so we answer these simple questions about ADS-CFT, and then we use that as input to generate this future and past region. Okay. Yeah. So this, yeah, because G has this feature, say, is bounded from below, so it makes sense to interpret the flow parameter generated by G to be a time. And we will see later this indeed corresponding to some kind of infalling time. I'll give you the kind of time slicing which can cross the horizon. Okay.
So Hong, just a quick clarification. You say evolution operators. So does that mean that there are many G's, or is G unique, or?
Right. Good. There are infinite number of G's.
Okay.
Yeah, yeah, there are infinite number of G's, but I will just pick a couple of very simple ones to explain some features, and then later I will explain why there are infinite number of such G's.
Okay.
Yeah. Okay, good. So now let me just give you an example of BTZ, which you can actually work out everything explicitly. In particular, I will just talk about one particular such G, and then we lead to one particular such kind of US. Okay, I just choose a simplest one. And so again, we are interested in this question. We take an operator in the right region and act on this boundary operator. We want to see. So this is intrinsically we can think of as a boundary operation. So this is some boundary operator, but have some kind of Bach interpretation. And then we just do this evolution on the boundary. But then we want to see how such evolution give you a sharp signature of a horizon. Okay. So it turns out, say let's start with s equal to 0. Okay, so you and increase s. Turns out that there exists an s0 which is greater than 0, and the following thing happens. So for s smaller than s0, so this operator starts from the right region, and then just by definition, actually. This operator can be considered as operator in the right T. Okay. And now it turns out this critical value of S0, once you cross S0, and now this phi evolved operator now contain actually both right and left degree freedom. Okay, so we interpret this as a sharp signature of the boundary for crossing the horizon. So the picture is the following. So imagine you have an operator on the right-hand side, starting from here, which at the beginning is just can be solely described by CFTR. And now if you have something take you behind the horizon, and before you cross the horizon, you can always be expressed in terms of the CFTR. But once you cross the horizon, you are in causal contact with both CFTR and CFT left. And now you actually, in the future region, then you must involve both CFT right and CFTL degrees freedom. Okay, and so we interpret this as a sharp signature of a horizon, the boundary from the boundary perspective. And in particular, you can generalize this notion. You can just even not think about the gravity side. We can just take any two quantum systems, and then let's imagine we can construct such kind of operator, some US, and then put these two quantum systems in the thermal field double state. And if you can construct such kind of US, and such kind of S0 exists, and then we can say, they're causally connectable in the sense, if we can try to interpret them have a gravity dual, then the gravity dual can be argued to have a horizon. Okay. Anyway, this is just a side remark. Say if you want to say verify whether SYK can describe quantum gravity, this may be a way to see, from the lab, to see a signature, sharp signature of a horizon. Okay. Good.
So in particular, this is true for any field theory for which I can form a thermofield double. So far, everything you've said applies to any system whatsoever.
Right now, this in principle applies to any system. And but we will see later, actually a sharp horizon, if you want to see a sharp horizon, you have to have some kind of large n limit. Say this sharp this sharp S0 is only possible when you have some kind of large n limit. And if you have a finite n, and then you will, yeah, it's more like a phase transition. Say if you have a finite volume, you can see a hint, say, of the phase transition, but strictly not speaking, it's not a sharp phase transition. Here it's similar. So in order to have this sharp horizon structure, you need some kind of infinite end limit. Yeah, but in principle, you can probe it for some.
So what about large n, but say like n equals 4 super Yang mills at large n, but small g squared n?
Yeah, in principle, you may see something like this. Yeah.
So something that we wouldn't think of ordinarily as being geometry.
That's right. Yeah. Something like this can happen. Yeah.
Thank you.
Good. So now let me say a little bit what is this S0. So so this operator is constructed intrinsically from the boundary theory. Okay, it just and it turns out that this operator actually knows the Kruskal time. Okay, yeah. For example, here let me just draw the Kruskal plane and forget about suppress the boundary and the singularity. So you should and suppose you start with a point x somewhere in the right region with Kruskal coordinate u0 and v0, and then when you act on this, it turns out that this S0 is precisely given by the minus U0. Okay. And for this particular transformation we choose, as I mentioned, there's an infinite number of transformations. So for one particular transformation we choose, and this S0 turns out to be exactly the minus value of, so U is smaller than 0 in the right region. So this precisely is the null distance in the Kruskal coordinates from that point to the horizon. And in particular, if you actually take your point very close to the path horizon, it turns out that this transformation is actually local. It just corresponding to a Kruskal law translation. Okay. But in general, for x at the general point not close to the horizon, actually the transformation is non-local. But so I have some finite spread. But even though it's non-local, but actually respect the causal structure. So for example, you can test how it respects the causal structure by looking at this kind of commutator. So you take an operator in the right region located at x1. So you evolve it by this US. And then you look at the commutator with the operator in the left region. So this coordinate axis for UV is the horizon. Okay, is the horizon. And so you see, again, that somehow even though the evolution is non-local, but this commutator becomes non-zero. Okay, so commutator is 0. Yeah, so if you want to have a commutator to be non-zero with this phi L, so you have to go into the light cone of this phi L, which is this region. And that means you have to go inside this region. And it turns out this is 0 when the S is smaller than this absolute. Yeah, again, it's it's this null distance along this U direction which controls this value of S. So when S is smaller than the distance to this light cone, and then you find this commutator is 0. But when S greater than this value, and somehow this operator now fall into this light cone. And again, you see this sharp light cone structure, and now you see the non-zero commutator. So
sorry.
Yeah.
So all this is for one of those specific operators that you see it very in terms of the Kruskal coordinates. Is that what you said?
Right.
That there's a special kind of an operator which corresponds directly to the Kruskal slicing.
This is not fully Kruskal. This is more like closely related to the translation along the Kruskal U direction, along the Kruskal U direction. And so this is one of the simplest. You can construct another one, say, which is closely related to the translation in the Kruskal V direction, which I'm going to also mention how to do that. Yeah.
And that would be more appropriate for the left side or something.
You can actually do both.
Okay.
So will we be careful here about how the operators are dressed? In particular, if one takes phi L to be the left Hamiltonian, So, depending on how one dresses the operator, one might find that either this commutator is 0 or it's non-zero. So is there?
Sure. This is just some generic scalar field operator on the gravity side.
Right, but even then one could ask, what if you take phi L to be the left Hamiltonian? So I mean, will this operator commute with the left Hamiltonian or will it not?
Yeah. Oh, for detailed question, of course, it's hard to say. Yeah, here we just only worked out the say some. Yeah, so Hamiltonian is a little bit tricky. So the Hamiltonian is a non-local operator. So here we are looking at the just some scalar fields or local scalar field operator in the block.
I see. Yeah, just to say the significance of that is that if one dresses operators to the right, so one runs the gravitational Wilson line to the right, then of course you do expect it to commute with the left Hamiltonian. But you can also dress operators in different ways so that they don't commute with the left Hamiltonian. But this was later important because it depends on whether one needs to have state dependence or not. But maybe I can again postpone the question till you present.
Sure. Yeah. Certainly these are interesting questions. Yeah. So here we just consider the simplest. Yeah. Good. So you can actually work out the whole flow pattern. So actually it turns out there's a surprise. So suppose we, yeah, so here there's so the boundary have a time direction, there's also spatial direction, and then in the block, so in this diagram, of course, the spatial direction on the boundary is suppressed. So now suppose you actually average over the boundary spatial directions. Okay, yeah, it just say just for simplicity, so that we don't have this kind of boundary, don't have this dependence on these transverse directions, so that we can concentrate on the Kruskal plane. And also, if you take the mass, say let's take this to be a scalar operator, a scalar field in the block, and let's take the mass of this scalar field to be large, means that the dimension of this operator to be large. So in this case, one can do some kind of, there's some kind of WKB behavior in the evolution of the phi. Then in this case, you actually find the evolution become local. Okay, and they just transform like this. So if you start with the initial point with U0 and V0, and then you find that this become a local transformation, give you U just translate by S, and the V translate by this. So the reason you have this, so one way to see you have this kind of structure is that this actually preserves the boundary. Yeah, so these have various features. For example, this transformation preserves the boundary, and etc. Okay. Anyway, so it turns out in this limit you actually find the local transformation, and so the flow pattern will be like this. So this is a flow. Just take one point, and then you take S to go to positive or negative, and then it will flow like this. Okay. And so this picture is the constant S slice. Say suppose we start with t equal to 0 slice, and then you evolve every point on this slice by this S, and then this will be a constant S slice. And you see this kind of slicing which crosses the horizon. Okay. And so these have the feature that near the past horizon, it's always just the U translation. Okay, because the V will be 0. And then just like just U translation. But in other point is a little bit more complicated, and it preserves the boundary.
Yeah, I have a question about the in the earlier three diagrams you shown that the global evolution of Cauchy slice, right? But the last diagram you showed that the infalling evolution of a bulk observable, right? The right, which is living in the right. So second is not a diffeomorphism invariant way of looking at the problem, right?
Sorry, say it again. Sorry, I didn't understand your question. Can you say the question again? I didn't hear very clearly.
Okay. So there were two diagrams. First one, I mean, which had three diagrams in it. The last one, which describes the Kruskal time evolution, is a global Cauchy size evolution, right? Yeah. But the second the last diagram, the last diagram you drew.
Yeah, so this is the counterpart of that. Yeah, so this is the counterpart of that. So this is a global slice, and then you can cross the horizon. Yeah.
But I think at some point you have drawn the single local observable time evolution also, right? Which is infalling in.
No. We are. I'm not talking about the. I'm not talking about the infalling time of a particular observer. We are talking about the evolution of a family of observers. Say imagine you have a family of observers on t equal to 0 slice, and then this U just evolve them according to this kind of time slice.
Okay.
Yeah, we're not looking at a particular geodesic motion or particular infalling motion of a particular observer. This just generates. Yeah, it just like in the Minkowski time, in the Minkowski space-time, the Minkowski time will generate a time slicing like this. Yeah.
Okay, thanks. Okay.
Yeah.
Are you going to tell us at some point how to construct this U of S?
Yeah, I will. Yeah, in the
Okay.
yeah.
And this UFS, it doesn't depend on phi itself, right? I mean, is it?
No, does not depend. So this US, this US will depend on phi, in the sense that this US it depends on all operators of your theory. You see, it's like you will see how we construct it. Yeah, so this US will depend on in the sense that all operators of your theory.
Sure. I mean, that, of course, in the no, I meant that you can use the same UFS with the same evolution for different field configurations.
Right. That's right.
And the different operators on the left.
That's right. Yeah. Here what I'm describing. Yeah. So the same US should do for every operator, but I'm describing the part corresponding to phi. Yeah.
Sure. Yeah, and that's fine. But it's the same UFS. Okay.
Sir, I had a question regarding the constant S slices, which is that if there's some quantum correction to the null boundaries via Hawking radiations, how will it change the S slicing?
Sorry, say it again. If there's a quantum correction to what?
If there's quantum corrections to the quantum corrections to the boundaries, to the structure of the boundaries and the sizes. I mean, like Hawking radiation. If there's a shrinking boundary or something like that, then how will the constant S slices change?
So here we are talking about the internal black hole, and the internal black hole it's an equilibrium state. The boundary does not shrink.
Yes.
Yeah.
Okay.
Yeah,
thank you.
Yeah, this is equilibrium state. Yeah.
Okay, thank you, sir.
Good. Okay. So yeah. So the basic. Yeah. Let me just use a cartoon to summarize what we. What this procedure is that start with the holography between the right, say, region of the black hole with the CFT-R and the left region with the CFT-L. By using this US, in the sense we can join them together into a full cross-cut diagram. Okay, so that's why we call this to be causal connectability, in the sense that that give you a genuine causal structure for the full space-time. And so this US leads to a new emergent infalling time. And also, as I mentioned, there's an infinite number of choices of such infalling times. And also this will be, since this is constructed from the boundary, there's so by definition it's diffeomorphism invariant. Okay, so now I will talk a little bit about the technique we will use to do this construction. And for that purpose, it's good to just review a little bit this entanglement in relativistic quantum field theory and the structure of this von Neumann algebra. So let me just first very quickly say how we normally say entanglement of a quantum system. Suppose you have a quantum system consists of 1 and 2 some subsystems. So in the standard quantum mechanical case, and then the full Hilbert space will be tensor product of H1, H2. So given this tensor product structure, then suppose you have a state defined for the full theory, then you can trace out, say, the degrees of freedom in system 2, and then get the reduced density matrix for system 1. And this reduced density matrix, of course, contains all the quantum information we want to know about the system, including the entanglement between 1 and 2. And yeah, quantum information science is about how to design all possible kind of observables which we can extract from this row 1. Okay, because the row 1 contains too much information. And so the simplest one is this von Neumann entropy, which is the you just do the trace row 1 log 1. Okay, so this can be characterized, can be used to characterize entanglement between 1 and 2. So now something special happens. If it turns out that this row 1 and row 2 are both full rank, okay. So if both row 1 and row 2 are full rank, then we can actually introduce additional structure. Then we can introduce this so-called modular operator, delta, which is defined by row 2 times row 1 minus 1. Okay, and yeah, so that's why we wanted full rank, because then we can take the inverse, and also the delta minus will involve the row 2 minus. Okay, row 2 minus 1. So when you have this modular operator, then this modular operator have a very simple algebraic property. You said if you say write it as delta IT with some exponential, some pure imaginary component, then that can take the operator algebra in the system 1 to itself, and similarly take the operator algebra 2 in system to itself. So here it's trivial because this delta is row 2 times row 1 minus 1, and by definition row 2 commute with any operator in H1. So this property is essentially trivial. Okay. And so this kind of flow is normally called modular flow. So when row 1 and row 2 are full rank actually means that the two systems actually are highly entangled, because if they're not highly entangled, then they don't have to be full rank. Okay. Say for example, if they're not entangled, then they will have just a rank 1. Okay, they have rank 1. And then we have just pure states. And so this modular flow actually then it's another way, okay, to see that this 1 and 2 are highly entangled. Okay. So this, of course, for quantum mechanical system, this is just some kind of, say, additional structure, which is kind of triviality. But it turns out when you go to quantum field theory, this is actually the only thing left. Okay, because in quantum field theory, we can actually not talk about reduced density matrix, etc. So now let me be a little bit more specific. So let's now talk about entanglement in quantum field theory. So let's just consider a quantum field theory in Minkowski spacetime. So you have, so now I separate into the right and left window regions, and then have a future and past regions. Okay. So this is just the, yeah, for simplicity, we can just consider 1 plus 1 dimensional Minkowski spacetime. But the same story applies to higher dimension. So it's often said that the Minkowski vacuum states, say if you consider QFT in the Minkowski vacuum state, that can be interpreted as thermal field double states for the right and the L Rindler patches. Okay. Yeah. So this is a heuristic way to understand, say, for example, why the accelerated observers have finite temperature, etc. And then this picture gives us lots of intuition and insight into, say, entanglement in quantum field theory. But strictly speaking, actually, this statement is not correct in the continuum limit. So this statement is only correct when you put the system on the lattice, okay, or you put some kind of brick wall between the left and the right, okay. And anyway, so in the strict continuum limit, actually, this statement is incorrect. But this kind of mathematical rigor normally does not make much difference for our physical considerations. And so for most questions, they don't matter. But for the questions we are interested in here, actually plays a key difference. Okay, so there are actually some fundamental differences between the discrete and the continuum case, and such differences actually will play a very important role for our purpose. So let's just compare. Okay, let's try to compare between the difference between discrete and continuum case. So a discrete just means you put the system on the lattice. Okay. And so so here you have local Hilbert space for the L and the right. Okay, because on the lattice by definition you have this tensor product structure for your Hilbert space. But in the continuum limit, actually such kind of factorization don't exist. So in a sense, just because any factorized states, they will have infinite energy. Okay, so physically, just any such kind of factorized states. If you have a factorized Hilbert space, then you must have factorized states. But factorized states actually have infinite energy when you have a quantum field theory, and so they are not in your physical Hilbert space. And also here, because you have
so you don't have factorized states, of course, in a continuum theory because the energy goes to infinity, but there is a notion of split states. So as long as you take a small scholar, there is a very close analog of the property, which is just a split property.
Sure. Yeah. I might mention this split property a little bit later, but at the moment it will not be important for our purpose.
Okay.
So you have this reduced. So if you have a factorized tensor product structure, then you can have reduced density matrix. And but here you don't have factorized structure, then you don't have reduced density matrix. Okay. And so here you have finite entanglement entropy in the discrete case, but in the continuum limit, this entropy just go to infinity. Okay. So strictly speaking, it's not defined. But in both cases, modular operator and modular flow exist. So essentially, that's the only thing in the continuum limit we can say, we can talk about entanglements between the L and the right region. Okay, and it is through the existence of this modular flow. But still, even in this case, there's a sharp difference between the discrete and the continuum limit in the behavior of this modular operator. So in the discrete case, this modular operator can be factorized. Just as I wrote earlier, you can write it as rho 2 and rho 1 minus 1. But in the continuum limits, it just involves the right and left equidistant in a complicated way. You cannot factorize them. Okay, there's no you cannot factorize the modular operator. So they couple in the complicated way. And here in the discrete case, there's no sharp light cone. Okay. And so this is reasonable. When you put the system on the lattice, there's always some kind of small tail, exponential tail, which can leak outside the light cone. Okay, but of course, in the continuum limit, we know there's a sharp light cone. So all these differences, including there's no sharp light cone in the discrete case, can be actually understood by a simple fundamental fact. Even though it's not obvious from those features, the simple fact is actually the operator algebras. If you look at the nature of the operator algebras in the right region, it turns out they have very different structures between the discrete case and the continuum limit. Okay, and turns out all these features can be just understood based on the different structure of their operator algebras, including the absence or the existence of the light cone. Okay, sharp light cone. And so this difference is that in the discrete case, it's so-called type 1 von Neumann algebra. So type 1 von Neumann algebra can always be formulated, say, as some kind of operator algebra acting on the Hilbert space. Okay, so this is just the standard story. But in this case, for the continuum case, so you have the type III1 von Neumann algebra. So I will not have time to go in detail the definition of the von Neumann algebras, how to classify different von Neumann algebras, etc. So let me just mention that these features, all these features, for the continuum case, can be considered, say, as some kind of physical manifestation, say, of this type III1 von Neumann algebra. So one important, let me just mention one important difference between them. So if you have a type 1 von Neumann algebra, then you can have a minimal projection. So means that you can take a pure state and write the density operator for that state. Then you get a projector, and that projector have rank 1. Okay, so you have a minimal projection. So, but for type III1 von Neumann algebra, actually there's no minimal projection. So any projection operator in this algebra is actually infinite rank. Okay, actually they can all be shown to be equivalent to identity. And so, yeah, good. Okay, so
I have a question.
Yeah.
Can I ask a question, Hong?
Yeah, sure.
Can you just go to the previous slide? So
Yeah.
are you saying that it is not possible to take a continuum limit of the discrete case to obtain results in the right-hand side? That is to go from type 1 to type III1? Or, I mean, there is no way of doing that?
No, I'm not saying that. I'm saying there should be a way to do that. You just say something very non-trivial happens in that limit.
Ah.
Yeah.
Nice.
Yeah, you should be able to do that. Just something non-trivial happens in that limit.
Okay.
So that such that the fundamental structure of this operator algebra changes.
Thanks.
Hi, can I ask a small question? So in ordinary quantum field theory, Minkowski spacetime also the algebra of local operators is type 3. So is this just that statement that that you are making, or is this something related to the
right? This is just a standard statement that the local operator algebra. Yeah, I'm going to actually just make this statement. Yeah, so this story, I think this is a statement maybe you want to make. Yeah, so this story is very general for relativistic quantum field theory. So for any local region, the local operator algebra, say after certain kind of completion, so can be associated with the type III1 von Neumann algebra. So this is actually just generic feature, okay, of relativistic QFTs, and yeah. So for QFT, essentially the only precise way, other than say, of course, you can always introduce some short distance cutoff, etc., and then you go back to the type 1 von Neumann algebra, and then you can talk about entanglement. But if you want to talk about entanglement in the continuum limits, and then the modular flow is the only structure. Modular flow associated with this algebraic structure, then it's the only way you can talk about entanglement. So it turns out that this type III1 algebra actually has some much richer structure compared to the type 1 case. Okay. And so one structure which I'm going to talk about now is this feature of the half-sided modular translation, which only exists for this type III1 algebra. So here I need to introduce a little bit mathematical term. So let's say consider M is a von Neumann algebra, and then you have a vector omega which is cyclic and separating for M. Okay. So let me just translate this sentence into the standard, say, our physical English language. So M you can imagine to be the right operator algebra for the operator algebra for the Windler right region. Okay, and this vector omega would be the vacuum state. Okay, so the statement that this vacuum state is cyclic and separating for M is heuristically is that when you discretize the system, that this operator algebra, this is the R and L, the reduced density matrix, say associated with omega is full rank. Okay, so this cyclic and separating is the fancy way in the continuum, to say in the continuum limit, which you don't have density operator, to say that the density operator and the density operator for your subsystem and its complement, they actually both full rank. Okay. So physically this is very easy to understand. So this is the condition. So in this case, then there's a modular flow operator. Okay. Now let's imagine. Now there's a von Neumann subalgebra of this M. Okay, so you have a lot of subalgebra with also a von Neumann algebra with the following property, that the omega is cyclic for N. So cyclic for N means that when you act N on omega, and the N is some operator algebra, when you act N on omega, and that you can say then after you take the completion, you can generate the full Hilbert space. Okay. And then another important property says, suppose there exists this algebra N, that if you do the modular flow of M on N, it does not take you outside N for one sign of the flow parameter. Okay, so that's why this is called half-sided. Okay, so for t smaller than 0, you do modular flow, you find the modular for M does not take N outside itself. Okay, and if such N exists, we say they exist. Yeah, if such a sub-algebra exists, we say there's a half-sided modular inclusion structure. Okay. So now suppose such an N exists. Okay. And now then it can be shown for some powerful theorem by Borchers and Westbrook in 90s, that for the type III1 algebra, then there exists a unitary group US with the following property. It said this unitary group can be generated by operator G, whose spectrum is bounded from below. Okay. So now this is maybe ring a bell from what I said earlier. So this is a way we can generate operator which is bounded from below. And in particular, this thing leave your original state, say leave your vacuum invariant. Okay. And so then this can be used to generate new times. Okay, so normally when you can write down a unitary group. So how do we in quantum mechanics, how do we distinguish time, say a unitary translation associated with time and a unitary translation associated with, say, a spatial translation or some kind of say internal symmetry? And the way we distinguish them is precisely that for the time translation, it should be associated with a Hamiltonian, and the Hamiltonian should have a spectrum which is bounded from below. Okay. So this property precisely ring a bell. So that can be used, should be able to help us to generate new times. Okay. So here just the key idea is from here. Yeah. So now let me give you an example. Okay. Again, using the Windler case as an example. So this is Windler. So now I draw using this Nightcon coordinate. This is x plus direction. This is x minus direction. So now let's take the M to be the operator algebra in the Windler right region. Okay. And now let's take this N, and then this is the type III1 von Neumann algebra. So from the result of this classical result in the algebraic quantum field theory. And now let's take the sub algebra to be the operator algebra in this region N. Okay, so essentially just shifted in this N. So this is a sub algebra of M. So obviously, and you can also check these two properties holds for this N. Okay, so omega here is just a vacuum state, and then the M is just the boost. So the modular flow of M here is just the boost, and when you boost this N. Under boost, you just do a law shift. So boost in this direction take N to itself, okay? But boost flow in the other direction can take you outside. So this have this half-sided structure, okay? And then this N satisfies this half-sided structure, and then there exists the operator G, which is bounded from below. And of course, G here is actually something we know. This is a trivial example. And here G essentially just generate the translations along x minus direction. Okay, it just corresponding to the law translation in the x minus direction. And so when you act, so now you can also act this U generated by G, which is a null shift on M itself. So again, if you S smaller than 0, take M to itself, and then in particular say normalize it so that when this S equal to -1, take M to N, so shift to this direction. But if I do a law shift in the S in that direction for S greater than 0, then that can take me M outside the original right region. Okay. So this way, by using this US, you can actually generate the future and the past region from the algebra of the right and L region. Okay. So this will be a way algebraically. Yeah, let me just try to finish this sentence. Algebraically, you can generate the full Minkowski space-time if I only give you the operator algebra, say in the right and the left region. Okay, and so in other words, starting with the Rindler time in L and R, so we can actually obtain the Minkowski's time. Okay, of course, this is like a trivial example. Yeah, but this will but this will be used as inspiration for how we would generate, say, Kruskal kind of time for the black hole case. Yeah. Yes.
Yeah. Sorry. So I'm trying to. So let's say we do something slightly different, which is what I was asking, which is we first generate the left wedge starting with the right by using the Bezonian-Wichmann construction. So we use this J operator to map all operators in the right wedge to the left wedge. And then we put the right and the left operators together to construct the forward and the past wedge. I mean, is this not exactly the same as the UFS we will get in this manner?
Sorry, say it again.
Yeah,
you
so
say you.
First,
Yeah.
I generate I'm given the right wedge. I generate the left wedge using the standard Tomita-Takisaki construction. So I write down a G operator, which gives me the left operators. And then I put together my left and right operators to get a forward. I mean, because the forward and past are, once I have both left and right, I can construct forward and past. So I sum together my left and right to get forward and past. It seems this will be exactly the same as what we would get by this G operator, right?
No. The idea is different, right? So if you start with R and L, indeed, if you use Minkowski evolution, you can generate the future and the past.
Yes.
But here we want the Minkowski evolution to be emergent. I don't want to use that as an input. I want Minkowski evolution to be emergent. And so that's why I need to use this structure so that I can have this emergent Minkowski time.
Yeah, I understand. But let's say I just took left and right, and I used that to write down formally a set of operators in the forward and the past region. I could just, you're right, I got them by Minkowski evolution, but later I can forget it and I just have a set of operators in the forward and the past. I'm struggling to, I don't see how it could be different from this from the UFS.
No, the result is the same. No, the result is the same, but the difference is conceptual difference. So the conceptual difference is that in the procedure you described, you used Minkowski's time. So our goal is not to construct an explicit formula, say, of the future region in terms of the right and the left. So that kind of formula was well known. You have done it before, HKLL, I have done it before for the black hole case. So our goal is not to construct that formula. Our goal is to understand the emergence of time. So previously, when people found such formulas, you have to use the analog of the Minkowski evolution in order to write down such formula. But what we want to do is that we don't want to start with use the Minkowski evolution as an input, because we want to understand how the Kruskal time evolution is emergent.
I see. Oh, okay. Just one more follow-up question. I mean, so the usual objection to this construction is that there could have been a firewall at the horizon. The state could have been entangled, but I could have had a shock wave coming just near the horizon. In which case, the state would, these Kruskal slices that we are drawing would not have existed. And that, I suppose, would be true here as well, right? If I took a state which was not Minkowski, but it was still cyclic and separating, but had a shock wave just near the horizon, then one would not see the shock wave in this construction, right? One would see a smooth interior by construction.
You should be able to. So that's a very interesting question. That's a very interesting question. Yeah, I will not be able to discuss that question in this talk, but we mentioned some comment related to that kind of question, and in the discussion section of the short paper. But unfortunately in this talk I'm not going to touch that question. I think you should be able to see that using this construction. Yeah. Good. Yeah.
Can I just ask a small question? So this algebra is the algebra of bounded operators. So it's a von Neumann algebra, but in the sharp horizon criteria you had the algebra of unbounded operators, right? Maybe it's a small difference for you. Just wanted to clarify.
So everything. So everything you should think of as a bounded operator. In order to be mathematically precise, so everything should be bounded operator. And then, but when I write explicit formula, I will not go through the procedure to make our, say, standard unbounded operator to be a bounded operator. I just assume that thing can be done, and will not complicate. Will not change the quality of the
thank you. Thanks.
Yeah, the picture. Yeah.
So can we do this for some simple example, like say free n equals 4 super Yang-Mills, or the symmetric product orbifold? What is this operator G in those examples?
Good. Yeah. So that's a good question. I think we cannot do it for free n equals 4 super Yang-Mills, but for weakly coupled n equals 4 super Yang-Mills might be possible, but will not be visible. May not be visible from perturbation theory. So you actually have to do really. So does not depend on weak coupling, but you cannot visible in the it will not be visible in perturbation theory. A finite order in perturbation theory.
But Hong, the theorem would still apply, right? Let's say I took free n equal to 4 Yang-Mills and I put in a thermofield double state. I would still have this family of operators which would generate for me this evolution, right? This G of, because this just depends on the entanglement structure. It doesn't care about the dynamics. So why can't we do it for the free theory? For free and equal
yeah, these are all good questions, comments. So I'm going to, so I will touch on this question a little bit later. Why somehow I think the free theory cannot do it. Yeah. So I will touch on this question a little bit later. Yeah.
Okay.
Good. Okay.
I have a question.
Yeah.
So if G generates translations along the x minus direction, I would understand that the point on the right-hand corner would translate along the x minus direction. But what about x plus? Where would that translate to?
Sorry, say it again.
X plus on your diagram. The point x plus on your diagram. Where would that translate to?
So this translates the whole slice, right? Just anything you translate into the you translate the whole slice. Yeah, just just X minus.
So for instance, where would x plus translate to if I apply e to the minus IGS? If it's a translation along the x minus direction, where would x plus translate to?
No, x plus is a number. It does not translate to. You have to
translate. The point in, I mean, for instance, an operator on x plus.
No, the x plus is the axis. What do you mean operate? You mean operate on this axis?
No. Okay, so x plus is an axis. I meant the point at the end of the axis. The topmost diagonal, the topmost point on the diagonal.
Oh no, is infinite, right? This axis is infinite, going to infinite.
Yeah. So a point.
Yeah. Any point, say on this axis, will translate along this x minus direction.
Okay.
Yeah. Okay, good. Sorry, I didn't look at the time. Yeah,
I think it's okay, Hong. It's late for you, but as long as you'd like to go on, we're fine. Please go on. Yeah.
Okay, good. Okay, good. So just to summarize this discussion, is that the key is that the type III1 von Neumann algebra and appropriately chosen subalgebras can lead to new emergent times. So now we will go back to the black hole and armed with the inspiration from this Rindler and Minkowski case to see how we treat the black hole story. Okay. So now we will do this black hole story. So to do that, we first have to see there's actually some additional structure should emerge. So black hole, is described by CFTR times CFTL in the thermal field double state. Okay. So here we are looking at, so if you look at the operator algebra, full operator algebra of the CFTR or CFTL, okay, we are not looking at the sub-region, we are looking at the full operator algebra. So by definition, this is type 1, okay, because this acts on the full Hilbert space. So, so this is type 1, even though, yeah, the type 3 happens in the quantum field theory only for local region, okay. Here we are looking at all space-time. And so, so this is by definition is type 1. But we argue actually for operator associated with the full space-time, there's actually an emergent type III1 von Neumann algebra in the non-GM image, which can lead to this emergent infalling times. Okay. Okay, now let me explain where this emergent type 1 von Neumann algebra comes from. So let's now consider the algebra generated by single trace operators of CFTR. Okay, so now these are only single trace operators. So essentially just take any single trace operators, you take product of them, you take sums of them, but you take, oh, of course, the number of products, you can take arbitrary number of products of them, but the number of products cannot depend on n. Okay, so that's how we, in the n equal to infinite limit, we can define an algebra associated with this single trace operator. And then acting, if you act this AR, say this single trace operator algebra on the CFT, say, yeah, so this is a single trace operator in the CFTR. But if you act this operator algebra on the CFT, the Hilbert space, then this is actually, you can show this is another von Neumann algebra. So I will not go into details. The reason is very simple, but you just, from simple definition of von Neumann algebra, you can see this is not the von Neumann algebra. But in the large limit, it turns out.
Sorry, Hong, just a small clarification. I thought you said earlier these continuum field theories have type 3 von Neumann algebras, but why do you say the operator algebra of the CFTR or CFTL is type 1?
Right. Good. Yeah, here's the key thing. This is the key. For quantum field theory, you have type 3-1 von Neumann algebra for any local region. So if you look at the algebra associated with some sub-region, that's always type 3-1. But if you look at the full operator algebra for the full space-time, that's actually by definition is type 1.
I see.
Yeah. So the type 3-1 comes from a sub-region. So here we're just looking at the full space-time.
I see. So earlier when you were saying you were talking in the context of the entanglement where you were looking at subregions. So that's why you were making a distinction between the discrete and the continuum with.
That's right. That's because we are looking at the Windler region. Yeah.
Okay.
But now for this thermal field double case, we actually need to look at the full boundary spacetime because we have 2 copies of the boundary theory, and then if you want to understand black hole, you actually have to look at the operator in the full boundary theory. Yeah, and then those operator algebra, they just trivial type 1.
Okay.
Yeah. Sorry, Hong, I have maybe a technical question at this point, which relates to Emil's earlier remark.
Okay.
So let's just take a single scalar field, so there is no large n.
Yeah.
But put it on an infinite spatial manifold. So the spatial manifold is non-compact.
Okay.
And we take a thermal state in that, just like this thermal field double. Isn't it true that the global algebra is still type 3 in that case?
No, in that case, it just yeah, I think in that case the global structure, the global algebra is still a type 1. It's because you can always yeah, it's type 1 infinity because you can.
I'm making a distinction between vacuum state of that scalar field theory and a thermal state. I thought in the vacuum, of course, it's type 1. Because see, the algebra, at least from the qubit construction, it depends on the starting state as well, right? The algebra you can get different algebras depending on the starting state. So in the single scalar field on R3, let's say spatial R3, I thought you get a type 1 in the vacuum, but it's still type 3-1 at finite temperature.
So the structure of this, so in that example, the structure of that operator algebra does not depend on, say, the states you act on, because you just act on the full Hilbert space, and the operator algebra always act on the full Hilbert space.
No, but the norm depends on the state you start with, right? The norm on the algebra. So because these are normed, like this Banach, whatever C star algebras have a norm, and the norm is defined using the starting state, and that can make a big difference in the structure of the algebra.
No, I don't have to. No, the norm does not depend on specific states. The norm is just, so this is just some operator in some Hilbert space. I have my Hilbert space. It's just some operator on the Hilbert space, and then the norm of those operators are just defined, not depend on specific states. It just depends.
I'm just referring to, for example, in sort of reviews that Edward has written, he makes this point that even if you take a StatMech system that has no large n, the only thing you need is some kind of thermodynamic limit, like either a large n or an infinite volume. The reason why these people in the 70s discussed the thermofield double was precisely this kind of a problem. So
right, yeah. So I have to read that part of the Edwards more recent paper.
For example, in this qubit systems, just an infinite sequence of qubit, it becomes clear that you can either get a type 2 or a type 3 from the same system.
Yeah.
It depends on the starting state.
Yeah, but if I just take scalar field theory, say on R3, and if I just so there might be some subtleties how you take the infinite volume limit.
No. Let's say we are always at infinite volume to start with.
Yeah. So there might be some subtleties in taking infinite volume. Yeah, but that will not be relevant for our purpose here. Here we can as well just take the boundary theory to be on the sphere.
Sorry, Repu, can I just say one thing? Let's say we just take the stress tensor and you integrate it on all of this R3. Right? So that'll give you the Hamiltonian. You can get the projector. In particular, you can get the projector on the vacuum, which is a one-dimensional projector. So it's a type 1 algebra, right? Because I mean the projector on the vacuum exists in this algebra once I include the whole space.
I mean the Hamiltonian is not in the algebra, so I don't know. It's an unbounded operator.
I'll take the projector on the vacuum, which is a bounded operator by construction. It's a one-dimensional projector.
Okay, maybe this is too technical for being in the middle of the talk. I can come back to it at the end. But
good. Raghu, I think this is a good point. I need to read that part of Edwards'
I think this is the essential reason for introducing the thermofield double, that even the full left-right CFT becomes like a type 3 at finite temperature. So there's a big difference between zero temperature and non-zero this thing.
Anyway. I can imagine something like that happens. Depend on how you take the infinite volume limit. Depend on how you take the infinite volume limit. But here, for our purpose, for the case of the black hole case, we can just say if we want to avoid that case, we can just take the boundary theory to be on the sphere, and I always take the infinite volume limit by taking that boundary theory CFT on the sphere and take some kind of infinite volume limit.
But the reason I was asking is because, like Emil was saying, you need a large n and a large gap kind of to see a clean horizon. So the construction, perhaps if it has both of those ingredients, it sort of just makes it richer, like if it has those things built in. But anyway.
Yeah, sure. But I think for this question, it will be not important because let's just say for simplicity, let's not worry about the infinite volume limits. Let's just think about the CFT is defined on the sphere, and then also we can define our infinite volume limit in a way so that this remains type 1. Which is actually the standard way we do the infinite volume limit.
I mean, so just to say one more time, even here, if we work strictly at n equals infinity, just the vacuum and the finite temperature algebra might be different, even if the spatial S3 and you take n equals infinity, right? Because See, in the single
Yeah,
trace.
no, I perfectly agree here.
Yeah,
No, I'm
okay.
not disputing that point.
Okay.
I'm not disputing that point. I'm just saying for the question, I'm not talking about the difference between the vacuum and the yeah, I'm just saying for this question, let's take the CFT to be on the sphere. And then in the thermal field double states, then the operator algebra with one of the CFT is type 1.
Yeah, in the vacuum, yeah.
Yeah, no, in the thermal field double state.
Okay, okay. Maybe let's come to it at the end. Yeah, okay.
Yeah, it's thermal field double state. It's type 1 when you're on the sphere. But then I want to argue there's an emergent type III1 in this structure. Yeah.
Sorry, Hong, can I ask a question? So just, I mean, the algebra is really, as you said earlier, not dependent on the, I mean, the state comes after you do GNS quantization. So whether it's algebra is type 1 or type 3 is whether you're looking at the local algebra or looking at the just algebra of all bounded operators, right? So,
sorry, say it again.
Well, the algebra is independent of the state. I mean, the state can come after you do GNS construction on an algebra. So,
yeah, exactly.
So the algebra is type 3 or type 1 doesn't depend on the choice of the.
That's precisely not true, right? That's
yeah,
exactly.
So, yeah,
that's definitely.
So that's the standard story.
Yeah.
So, Raghu is saying there's some additional subtlety in that. I can imagine there might be some subtlety in that. Just at the moment, I think it will not be important for what I'm going to say. Yeah.
Okay. Hong, I have just one more question. So this, when you say algebra generated by single trace operators and CFTR, I mean, again, just to make sure it's the bounded operators generated by these single trace.
Right.
And then when you say it's not von Neumann, so I mean, it's a double commutant. What are the elements in AR which are not in the double commutant? I mean, is there an easy way to understand? It's very complicated.
Yeah, because the double commutant of the AR is not single trace operator. It's actually the full operator in the boundary theory.
I see. Okay.
Yeah. Because you can have those complicated operators which outside the single trace algebra in the double commutant.
Maybe you defined it earlier and I missed before, but can you please again reiterate what a type III1 von Neumann algebra means and what a type 1 algebra means?
No, I will not be able to define it precisely. It takes time to do it. So type 1 von Neumann algebra is the one with with only infinite projections. Okay, and every projection are equivalent to the identity.
What do you mean by projection?
Just projector.
Yeah, there can be all sorts of projectors. What do you mean by projector?
Perhaps we can keep general discussions to the end of the talk because we are already past.
Right. Yeah. Projector just means the projector. It just all the projector in this algebra, they are infinite rank.
Can you give an algebraic definition of a projector?
It's just P squared equal to P.
And in terms of the states of the Hilbert space, what would it be?
No, it's just P squared equal to P, and then yeah, that's a projector.
Okay.
Yeah. Good. So so in the large n limits, so you see the key thing is that the definition of the von Neumann algebra actually depends on the kind of Hilbert space you act on. So it turns out in the large n limit, there's another Hilbert space, which is the Hilbert space of small excitations around thermal field double states. Okay, so heuristically, you can imagine just you act all possible single trace operator algebra. Yeah, you can act this single trace operator algebra on the thermal field double states. And heuristically, you can imagine that that kind of action, the states you obtained from that kind of action have a Hilbert space structure. Actually, this structure can be made precise. Okay, you can actually just act in the single trace operator algebra on the thermal field double states. You can mathematically really construct a Hilbert space. Okay, so this is normally called the GNS construction. So this GNS construction, you can construct the Hilbert space say around the thermal field double state. And then the representation of single trace operator algebra in that Hilbert space, okay, in this GNS Hilbert space. So I want to emphasize that it's a representation of this algebra in that GNS Hilbert space. Now I call it MR. And now this operator algebra, I conjecture, we conjecture R type 3-1. Okay. And so there's various support for this. So including the thermal spectral function of single trace operator. So Emo, so that's related to your earlier questions whether free theory can do it or not. So in order for this to be a type 3-1 algebra, so type 3 algebra have certain spectral properties. And so if you have a free theory, free equal Yang-Mills theory, if you look at the 2-point function of the single trace operators, I don't think they satisfy the spectral properties required by the type 3-1 algebra. Anyway,
is there some statement that the spectrum needs to be sufficiently chaotic that it satisfies?
Yeah, so there's a precise statement.
Properties and so on.
There's a precise statement is that if you look at the modular you have to look at the spectrum. Yeah, look at any operator. Look at any states in your Hilbert space which support this modular operator, and which have modular operator, and then you look at the spectrum of that operator. You look at the spectrum of that modular operator, and then you look at the intersection of all possible such kind of spectrum. And then the statement that if it's type 3-1, then that spectrum will have to cover the full real axis. Okay, the full real axis. And anyway, so let's go to a bit technical detail. We mentioned something of this in this non-paper. And anyway, so we believe that the free theory don't satisfy this property.
Hong, can I just say maybe the free theory doesn't satisfy it, but at arbitrarily weak Toff coupling, it probably will satisfy it for the black hole state, right?
That's right. Yeah, I believe that arbitrarily weak coupling should satisfy, but you cannot do this, but will not be readable in perturbation theory.
Right. But I think Emil's, at least the spirit I thought of Emil's question was that at weak coupling, the geometry is not something which is nice and straightforward, but at weak coupling, these properties will probably be satisfied, even at arbitrarily weak coupling.
Yeah, that I perfectly agree. Yeah. And then also, as I mentioned, that the type 3, this half-sided modular inclusion and translation structure only can happen in the type 3-1 structure. So we have a constructive way to do this kind of structure. And anyway, so this is another support for this thing. And the third one is duality with the box. So let me just mention this duality with the box, which is the most intuitive way to think about it. So let's think about the operator algebra in the box in the context of treating the box as a quantum field theory in the curved space-time, because we are looking at the n go to infinity limit. And when you go to look at the n go to infinity limit in the box, is essentially you doing perturbed expansion in G Newton, and then you can construct the Fock space of the Bach fields around the Hawking vacuum. And then you have operator algebra of the Bach field in the right region and in the left region. Okay, so I call them F tilde M, F tilde L. So the standard duality between the story outside the horizon and the boundary CFT at finite temperature then can be phrased as you identify this GNS Hilbert space, say of created by single trace operator with this Fock space in the black hole geometry. And the vacuum, yeah, so this is there's a vacuum state for the GNS Hilbert space identified with the Hawking vacuum. And then the operator algebra of this single trace operator algebra acting on the GNS Hilbert space and map to the operator algebra in the Bach. Okay, so it's this picture. So this duality between outside the horizon can be expressed using this operator language in terms of MR, is that should be identified with M tilde R. Yeah.
Can I ask a question here, Hong? So if I'm understanding correctly, I think what you're calling the GNS space is what we were calling the little Hilbert space, and that you take the thermofield double state and just act on it with a set of all operators. Of course, in this, for us, we just truncated things because we were at large n, so we were working with what you would call type 1. But maybe one question that's related here is, let's say I take not the thermofield double state, but the thermofield double state evolved on the left side. So I take e to the power I HLT on the thermofield double state. That's a cousin of the thermofield double state where a large diffeomorphism has acted on the left. My understanding is that the HGNS that you will get in that way will be distinct, right? It will be a completely different space from the one you got from the original thermofield double state. Is that correct?
Sorry, so you want to add a left translation on the left, on the GNS?
Right.
Yeah, you will get a different GNS Hilbert space. That's right.
Right, but it will be orthogonal in this limit that you're looking at, I think, to the original space. Like it's just a totally different space.
Yeah, it is a totally different space. Yeah.
Right, but it'll be exactly orthogonal in the infinite end limit, right? Is that? I think it.
Yeah, I'm not sure whether they will be exactly orthogonal, but I think yeah, agree. Yeah, yeah, I have not thought about it very carefully, but I say intuitively I agree with your statement. Yeah.
Yeah. Thank you.
Good. Okay, so and then now because the ML and the MR, they just operate algebras in the sub-region in the black hole geometry. Okay, so by doing the duality, then we know that, yeah, by just looking at quantum field theory in the curved space-time, so they corresponding to some sub-region in the black hole geometry, then they should be type III1. Okay, so that's another way to support this to be type III1. Okay, so now we have this picture which is identified. Now we have to find the sub-algebra. Okay, so now we have found this emergent von Neumann algebra in the boundary, type III1, defined for the full space-time. And now we just need to find the sub-algebra which can generate this infalling time for us. Okay, and so let me just make some remarks here. So where these theorems of half-sided modular translations, which they ensure the existence of such kind of translation, but finding it explicit in general is very difficult. Okay, it's yeah, they show the existence, but if you want to construct it, it's actually not easy. It's complicated. But here in the Nagian limits, we have a great simplification because the algebra of single trace operators in the GNS Hilbert space can be actually described by that of a generalized free field theory. Okay, and so in this context, the structure becomes greatly simplified. So in this case, we can show. So this is some highly non-trivial statements that the expression of this US, okay, acting on this generalized free field theory, have a universal form, say up to a phase factor, which depend on the specific algebra. Okay, so by the expression of US, I mean just the action of the US on the field operators. Okay, you can determine the form. You can determine it to a universal form up to some phase factor, and this phase factor it depends on your specific algebras. And in the sense, different algebras they all come in just with a phase factor. Okay, so that's the part which depends on it. Okay, so another general remark is that if you look at the causal diamond and look at the operator algebras associated with a Cauchy slice of a causal diamond, so if you have an ordinary quantum field theory, then the algebra associated with the slice A1 and this slice A2, they are equivalent, okay, because they're just related to evolution of each other. But for the single trace operator algebra, they are actually not equivalent. Okay, because the standard Hamiltonian evolution take single trace operator algebra outside the algebra. Okay, and so if you evolve this A1 using Hamiltonian evolution, it's standard Heisenberg evolution, and then actually that takes you outside the single trace operator algebra. And so A1 and A2 actually are not equivalent. So this also can be easily understood from the perspective, say, in the general free field theory perspective. So generalized free field is defined for the full space-time. There's no equation motion governing the behavior of generalized free fields. So the algebra associated with one slice and algebra associated with another slice, they're just inequivalent. Okay. Good. So this is a key point. Okay, this is a key point. And now with this key point and the earlier preparation, we can just tell you how we can construct boundary times, emergent boundary times. So let's say, for example, let's draw this 1 + 1 dimensional space-time. The vertical direction is time, and the horizontal direction is space. We can imagine this series on the circle. Okay, we can imagine this series on the circle, and so the boundary series on the cylinder. And then the full algebra would be just the full single trace operator algebra for the full space-time. So this is our M. So this is single trace operator algebra for the full space-time. And now I take the sub-algebra N to be the single trace operator algebra below certain time. Okay, so cover this space-time region. So up to some time, for example, t = 0. Okay, so this is the sub-algebra. And also here in the sum of your double states, the modular flow is just the ordinary time flow. Okay, because this, and then this N trivially satisfies this half-sided structure. So this will give you an emergent new time. Okay, so this M and N will give you a new time. And similarly, you can take N to be the upper half of your boundary space-time, or you can actually have choose the slice so that it's not uniform along the spatial direction. Okay, and this can also, yeah, it can have infinite number of such N's. So in principle, we have infinite number of such emergent time. Okay, you can also do that. So now let's just consider the simplest case corresponding to you take N to be just say all the operator algebra below t = 0. Okay. So now even at the generalized free field level, finding this US is actually strongly coupled problem because it's anyway, that involves finding the modular operator for this. Yeah. So this even at the generalized free field theory level is not easy. You need some information about two-point functions of your theory at strong coupling. Which due to the bulk. So now we have
a question.
Yeah.
So is it to be understood that ML and MR and M tilde and MR are defined in say ML and MR are defined on the boundary space-time, and ML tilde and ML tilde are defined on the bulk?
Yeah, that's right. That's right. Yeah.
So S is to be understood as a bulk coordinate, right? In a
so
certain
X
sense?
is, yeah, X is a bulk coordinate. That's right. Yeah.
Yeah. So the extra bulk coordinate is S actually. It parameterizes the bulk direction.
Yeah.
In a certain
it parameterizes. Yeah, it parameterizes a point outside the horizon, operated as a boundary operator. Yeah.
Yeah. Okay.
So one can ask, in terms of finding it explicitly, why don't we do what we were discussing earlier, that we first do the Tomita-Takisaki to get the left, and then we write down formally the expressions you would have obtained by global bulk evolution. And I in that way using the bulk, but in the end it's just an answer for what U of S is. So
yeah,
I mean that will give us an explicit construction of U of S, right?
Right, but we want to understand how this spark time emerges, right? So I want to show intrinsically somehow if I do this kind of thing, that will actually generate a non-trivial spark time.
But the theorem just tells us about the existence of a U of S, and now we'll write down a U of S which is explicit in this way, right? So there's no, I mean, the theorem guarantees the existence of U of S, and now we'll write it down by doing this construction.
Yeah. So this guarantee you generate a US, but we have to verify this US indeed generated this infalling time. It's actually U falling does not only take you outside the horizon.
Right. Okay.
We have to verify that.
In that, you would like to verify that it has a spectrum bounded from below, for instance. That's
yeah. The spectrum is bounded from below. That's guaranteed by the theorem.
Right.
But we want to see. But we want to see this actually is an infalling time.
Okay. Okay. Thank you.
Yeah. We want to see that is infalling time. So if you want to construct this US, the action of US explicitly is actually still non-trivial. And so here we use a trick. Okay, here we have a proposal. So we propose that the operator algebra in this N region, which is the operator algebra below sometime in the boundary space-time, we propose that this is actually dual to the operator algebra in the Bach region in this causal wedge of this N. Okay, we call N tilde. Okay, in the causal wedge of N. And now this, so now they become equivalent. And now in the Bach, I really have a genuine free field theory. Okay, so boundary I have a generalized free field. This generalized free field contains strongly coupled information. Okay, but in the Bach now I have genuine free fields, and now I can actually work out the phase factor which go into this US. So turns out this phase factor, which we need to determine this action of the US, is given by the phase shift at the horizon. So remember, yeah, for those of you who are familiar with just the scalar fields, say in the black hole space-time, say write your scalar fields, say in terms of the Schwarzschild coordinates, and then when you go, say in terms of the torus coordinates, and when you go to the horizon, then the horizon is just two plane waves, ingoing wave and outgoing wave. And if your field is normalizable on the boundary, and if your solution is normalizable on the boundary, and then this ingoing wave and outgoing wave, they differ by specific phase shift. Okay, turns out it's precisely that phase shift which go into the this US. Okay, this US. And anyway, so now you can just now we can construct this full US, the action of this full US on such a generalized free field. And
I have another question.
Yeah.
Can you? Yeah. Yes. So initially, in one of your previous diagrams, you had this entire boundary going over to the x minus axis, right?
No. That's a toy example. That's just the no. You're talking about which example?
Yeah. So no, in one of your previous diagrams where you showed the pattern of the boundaries getting deformed into other boundaries. In that diagram, you initially the right boundary, the one on which n lives, that actually maps to the diagonal along x minus, right?
No. Yeah, you're talking about this diagram?
This one. Yeah. So yeah, this one, the left one, the left diagram.
Yeah.
You can see the curves on the right, they're slowly deforming to a diagonal which is along U.
No. Here I'm drawing the Kruskal diagram. So this black line is the boundary. So the boundary is just always like that.
Yeah, but when you act upon them by e to the minus gs with increasing amounts of s, don't they deform to all these different?
No. So that action, when you act on the boundary, it just stay in the boundary.
So then what do these extra diagrams mean? Extra curves mean?
Oh, that means the action on the Bach operator. So
okay.
So any operator on any point, I can treat it as a boundary operator from our standard ADS-CFT applied to the region outside the horizon, and then that describes how this generates the flow of those operators.
Okay.
Yeah. Anyway, so if I choose this one, then using this trick, so there's various consistency check that this proposal is actually correct. So I will not have time to describe here. Anyway, so that's the way we generate this kind of flow path. Okay. And then you can do this one, which n corresponding to, say, t greater than 0, and then can be argue to the block slice like this, and then that will generate a flow which is more like a v flow. Okay, so along the v axis is actually translation, and then in other anyway. You can also compose them. Okay, you can compose consider compositions of such cross-cut u and v type flows, and then that can generate more intricate patterns.
So
and you can also, looking at any of this kind of curved, any other this kind of n I drew earlier, then you can generate infinite number of times. Yes?
Yeah, the question is, so it's a question I asked earlier. So let's say we take not the thermofield double state, but the thermofield double state after the action of a unitary operator on the left CFT.
Yeah.
Then it seems to me that everything that goes into the construction that you described will be unchanged, because you take the right algebra, all inner products, all expectation values are unchanged. And therefore the
it will change.
Yeah.
It will change because the yeah. So you're asking whether the existence of this u left can be felt.
Yes.
Can be felt by the yeah. So yeah, it can be felt, and that's precisely this discussion which I referred to you earlier. So we discussed in the conclusion, in the discussion section of this short paper. And so the quick statement, he said you should divide it into, say, whether UL is big enough to generate, say, geometry, or UL is in your the box space of your black hole. So in the case which you change the geometry, and then of course that you need to redo S Hilbert space. You just get a different JS Hilbert space, and then you have to redo that.
But how does GNS Hilbert space change? Because you're only acting with the right signal trace operators, and all expectation values of those are unchanged. So why would it? Why would it change on the right?
Right. So the JS Hilbert space. So the JS Hilbert. So JS Hilbert space says JS Hilbert space itself does not change, but the representation of the left algebra on the JS Hilbert space does change. Yeah.
Okay. Thank you. Yeah. So indeed. So that's of course true that, you know, if you but I have a feeling that this construction then you're right. You'll get a different left algebra. But I have a feeling that this may not give the right operators that one would get from the bulk. I mean, this is the standard objection to the Tomita-Takisaki construction, is that you're right, of course, if you have a slightly different entanglement pattern, then the representation that you get of the left operators changes. But that is not that's not exactly the right operators you need in the interior. We can discuss it more if you like. But yeah,
I think certainly this is an important question. So I feel this is not a problem, but we didn't look at it in great detail.
Okay.
So we have some argument which will be outlined in that part of the discussion. Yeah.
Okay. Thank you.
Yeah.
I have another question. This e to the minus IGS, this operator, this you said generated translations along the x minus, right?
Yeah.
So is that that
you can either x minus, you can either u type or v type, or you can do infinite many others. Yeah.
Yeah. So is it to be understood that as s varies from, say, from some parameter to some other parameter, the transformation of some point on the boundary goes through different points in the bulk?
No. The feature is that it always take a boundary point to another boundary point. It does not.
In that case, how is e to the minus IGS actually generating the bulk?
It's because we start with the region outside the horizon. So because from the standard story in the ADS-CFT, we understand how the right region in the black hole geometry can be understood as, say, part of the right CFT. Okay, so we already know that part of the story in terms of the right CFT. We use that as a starting point to understand the region inside the horizon.
So in that case, how is the e to the minus IGS generating the MR and MR tilde and ML tilde from the MR and the ML?
No, they're equivalent. They're identified under the duality. No, MR and MR tilde, they are identified under the duality. So exponential IGS act on MR, so you also act on R tilde.
But they are in different spaces.
No, they are the same space. They're identified under the duality.
But you said the one is defined in the wedge and the other is defined on the boundary.
Yeah, but they're identified from the ADS-CFT dictionary.
Yeah, so for the wedge region, the operator dependence, the operator definition would be different from that of the boundary.
No.
Because it acts on the bulk degrees of freedom.
No. They are just the same algebra. Any operator in the right region can be expressed in terms of the operator on the boundary. So by definition, that's the operator on the boundary.
But the degrees of freedom on the boundary are different from the degrees of freedom in the bulk, right?
No.
That's from the ADS-CFT correspondence.
No, from ADS-CFT correspondence, they are the same.
So could I request maybe we postpone this discussion to later, and then we can let Hong go on with the talk.
Right. Okay. Good. Okay. Yeah. So
yeah. Can I ask a question? Sure. Hi. At some point, you also had this prescription for bulk Schwinger-Keldysh contours to describe, like, to do some real-time calculations in ADS-CFT and so on, right? Do you have any comment on, like, approaching this kind of problem from such a configuration of the bulk geometry, like, or does that make sense? As in I'm asking in the sense that, like, you could always think of a purification in terms of TFT or something, but is there a way to think of this bulk constructing these interior points from the Schwinger-Keldysh contour itself, or do you have any comments on that?
Yeah, I don't know. Yeah, I don't know the answer. I don't see a direct connection. Yeah. Good. Okay. Yeah. Let me just very quickly. Yeah, it's getting very late. So I'm talking too long. So yeah. Yeah. I mean, say I'm way over time. So this type III1 is actually ubiquitous. This emergent is not just in the thermofield double case. We can also consider the case which we just consider the boundary safety in the vacuum. Okay, you consider some region R in the boundary. So then there's a standard story. If you look at the full operator algebra in R, so this is type III1. Okay, so this is just the CFT operator algebra in this local region. It should be type III1. But now we want to argue there's another emergent type III1 structure. So this emergent type III1 structure, again, you look at the completion of single trace operator in this R, okay, and we claim that's an emergent type III1 in the larger n limits, okay. And so this type III1 algebra leads to actually two different types of divergences in holographic entanglement entropy. Say the first standard one leads to just the standard divergence in the Ryu-Takayama formula near the boundary. Yeah, just the area is always divergent near the boundary. And this emergent type III1 are associated with the entanglement and divergence of the entanglement entropy in the bulk, in this entanglement wedge region across the RT surface. Okay, so that entanglement entropy corresponding to an entanglement entropy of a quantum field theory in the bulk, and that have some UV divergences, and that's related to this emergent type III1 structure. Yeah. Anyway, so here let me just make some quick comments. So here, I gave you some explicit construction of some kind of infalling time. You can also ask a general question. Suppose here I want to describe some kind of slice, some kind of emergent time, emergent infalling time, give this kind of slicing in the bulk. Okay, what are the necessary conditions test to satisfy? So suppose, yeah, just let's consider this question abstract. And the first, G certainly have to involve both R and L discrete in a non-trivial way, because if you will have to cross the horizon, then you have to be in causal contact with both L and R. So it has to involve both R and L in the non-trivial way. And also, as I mentioned, at the time, the spectrum should be bounded from below. Okay. So now it turns out, just given these two properties, okay, just given these two properties, you can argue that the sharp horizon cannot exist at the finite end. So the basic idea is that the finite end, you only always have just type 1 algebra. Okay, so this emergent type III1 algebra is just emergent in the infinite end limit, or you do perturbatively in one of them. So if you have a strict finite end, and then you can show that such kind of sharp horizon cannot exist. And so this is very similar to the situation of a discretized quantum field theory cannot have a sharp light cone. And there you just have a type 1 algebra. And then you can show that you cannot have sharp light cone, just due to the algebraic structure. And so let me just very quickly mention some points, or I can stop here, or whatever people prefer. Yeah.
You can maybe briefly tell us what in this section.
Sorry?
You can take maybe 5 more minutes.
Okay, yeah. And let me just do very quickly mention some point.
Sure.
So first is that the issue of black hole singularity. So the existence of black singularity you expect when you evolve this U at certain point, somehow this evolution should become singular. Okay. But so we have been looking for this kind of singular behavior for quite some time, but turns out somewhat subtle to see. Okay, it turns out somewhat subtle to see. So we have not found such a sharp signature, even though we have seen indications that this U evolution does stop at some finite S. Okay, so you cannot extend to infinite value of S. Not like in the Rindler. In the Rindler, you can extend to infinite value of S. So here we see indication that it stops at the finite value of S, but to map that S precisely to the singularity turns out to be subtle. Okay, so here I don't have the full answer. And but anyway, the conceptual picture is rather clear. Is that now we can interpret that the appearance of the singularity in the gravity geometry is actually signal, is the gravity way to tell you, okay, there is such an emergent type III1 structure. Okay, so if this structure is not emergent in the infinite end limit, then you can always, then you should be able to have low problem extended to infinite, okay, infinite the value of S. And the fact that somehow this should stop at some finite value of S tells you somehow that this structure, so this is the one way. So give you so this can be viewed as a new perspective to think about the singularity of the black hole.
So
and
can I
also provides potentially provide some way to understand the resolution of the singularity.
So can I ask a question, or see? So is there a way of characterizing the singularity in the bulk in terms of something going wrong in the boundary theory at n equal to infinity, something becoming singular, some correlation?
Yeah, exactly.
Some objects.
So so what we wanted to see is that you act, say, you act this U on some boundary operator, and then that corresponding to you take that operator, go through the horizon into the interior, and then you find that for some finite value of S, that kind of revolution becomes singular. Yeah.
Nice.
So that would be considered as an indication of the singularity.
Okay.
Right. Okay, good. So also let me just make some comment on this Bach divergences. So we have this type III1 algebra in the boundary, emergent type III1 algebra in the boundary theory. So this emergent type III1 algebra, in some sense, only depend on the large n. So as far as you have infinite n limits, you should have this type III1 algebra. Even if you treat exactly, no matter value of lambda, okay, no matter value of lambda, then that seems to be rather peculiar when you translate into Bach language. So as I mentioned, this type III1 algebra implies that the Bach entanglement entropy is actually divergent, okay? And so this means that even if you can calculate this Bach entanglement entropy using string theory, means you include all alpha prime corrections, which means that you can calculate on the boundary exactly in lambda, not doing 1 over lambda expansion, etc., exactly in lambda. You still see a divergence. And divergences can only cancel between different, when you do everything in finite n. Okay. So that's rather surprising, because normally we think in the Bach, say if you calculate using string theory, you should be finite, okay, genus by genus. Okay, at each genus of string theory calculation, you should get a finite answer. But this suggests that actually, if you use string theory to calculate this kind of entanglement quantities, you actually will get some divergences. You cannot get finite answer genus by genus. Okay. Yeah, so this is the comment here.
Oh, can I ask you a question?
Yeah.
Yeah. So are you saying that? Okay, then how do you define this quantum extremal surface? I mean, if this part entanglement is divergent.
So just look at the black hole case. So black hole case, the black hole entropy is the sum. Yeah. So the boundary entropy, so the boundary thermal entropy is the sum, say, of the, yeah, if you do perturbatively in Newton expansion, will be the sum of the horizon area, then add the Bach entanglement entropy, which you can calculate, say, perturbatively in Newton, and start with 0th power in Newton, that kind of entanglement entropy. And so only the sum of all the sum of this genus 0 piece, which is the area term, and plus this the genus 1, etc. Only the sum of them somehow is convergent. Separately, they are divergent.
But G Newton is finite in string theory, order by order in perturbation theory, right?
Yeah, so that's the puzzling thing. Say if you try to calculate this kind of entropy, say in string theory, suppose we can calculate it genus by genus, just calculate the genus 0 and genus 1, etc. Seems like this picture tells you that somehow they will not. Somehow you have to add them. Yeah.
But it's not a cancellation between the two terms, right? Because the area over G Newton seems to be finite, genus by genus, because G Newton is finite, right?
Yeah, I don't know. I don't know. Yeah, so I don't know how to precisely phrase this question. It just seems like somehow this Nagian, this emergent type 3-1 only depend on Nagian. So yeah. And only when you do finite n, which is then you go to type 1, and then you have a well-defined entropy.
Okay, thank you.
Yeah. So my own speculation is that somehow when you calculate this kind of entanglement entropy in the bulk, somehow the genus 0 piece may not be separately convergent. Yeah. So you may need some cancellation between genus 0 and genus 1, etc. Okay, good. And then of course we should understand better this emergence of this type 3-1 algebra in the infinite n limits, and including the emergence of singularity and the revolution, and also also I think this emergent type 3-1 structure could lead to many things, not only just emergent time. For example, they can lead to us understanding some emergent symmetries, some symmetries which actually not exact when you treat the G Newton as exact, but only appears in the G Newton goes to infinity limits. For example, there's some indication of this in the JT gravity, which due to SYK. So this SL2R symmetry described by various people actually can be such kind of emergent symmetries. Anyway, so also symmetries associated with the horizon, and likely they are just the emergent symmetries which are not exact at finite end. And also, yeah, of course, to generalize to single-sided black holes with Suvarat and the Papadimos, and their paper should be relevant. And then maybe there's also give us some hint how to treat for cosmological case. And yes, I will stop here.
Thanks. Let's thank Honglu for the wonderful talk. Very clear. Thanks, Hong. Maybe we can take one or two quick questions. Must be pretty late for you, right?
If I may, like just on the previous discussion, that I think it might be interesting to separate, the large n from infinite volume, precisely because of some of the questions on this slide. I think that after I also put a sentence from Edward's paper in the chat, and it really is true that even if you work at infinite volume for just a single scalar, the algebra just of the right is a type 3 algebra. And you see, singularities and so on are maybe more of a, to go to the next, it just might be helpful to really distinguish these two cases, like either n equals infinity or spatial volume equals infinity. And
so certainly certainly I think we should separate into these two. Certainly we should separate them
because I think that the existence of this operator you will have even in the infinite volume case, but there it is probably not telling us about black hole physics in the bulk.
Yeah, so indeed, so I think the so at least for the black hole story, we can avoid this infinite volume case.
I understand.
Yeah. So indeed, certainly, and also normally when we do the infinite volume in ADS-CFT, it's always should be considered as, say, some limit of we take this field to be large, and it's always you first take the infinite and limit. Yeah, so I think what you are emphasizing is that the which in some cases there may be exchange of limits. When you take n go to infinity and the volume go to infinity,
yeah,
depending on which
even
you
if we keep
first.
n finite, just n equals 1 and take volume to infinity, you will still get the same structure, like basically like you have described, because it's just tied to the algebraic construction of the thermofield double and the GNS on top of that.
That I'm not sure. Yeah, so that I have to think about more carefully. I have not thought about the infinite volume case.
Okay.
Much more carefully. Yeah. So I want to think about the infinite volume case more carefully. But just in the standard ADS-CFT, we always take the infinite n limit first, and then take the large volume limit.
Yeah, exactly. And the reason I'm saying it is because you have these singularities and so on that are still to be understood, and it might shed light on those questions, like what is special about this particular, anyway.
Yeah, certainly I think infinite n. So if there is some kind of type III1, say for the infinite volume case,
yeah,
and this infinite n and this large volume, they should be very different nature in the sense.
Exactly, because in the infinite volume, you probably don't have the singularity, right? Just if n is finite and.
Yeah, presumably we don't have
exactly.
it. Yeah.
So that,
yeah. So yeah, but I think in the infinite volume case, in the sense you have to define that limits carefully in order to get this III1 structure. If I just take the torus, naively take the limit, and I think you, just that limit is very tricky to define.
I think the limit is similar to what you're saying, that the products, you should not take n squared amount of product. Then you should not take a string of operator which is stressing across the whole torus. So, the operators you get are kind of localized in space. That's the kind of operator algebra you will get, not something that is stretching across the whole, spatial this thing.
Yeah, that's right. Yeah. So you have to define that limit carefully. Yeah, I can certainly imagine something like that. Yeah.
Okay,
just we haven't thought about the infinite volume case.
Thanks for the very nice talk.
I have a question.
Okay.
Yeah, so it goes back to the question that I was asking. How can you exactly generate bulk physics by applying unitary transformations on the boundary physics?
Right. Yeah. So I think I don't have much more to say than what I already said. Is that any operator in the outside the horizon from our standard ADS-CFT dictionary, they are regarded as a boundary operator. Yeah, that's all I can say.
Do you have in mind some sort of HKLL type construction to relate?
Yeah, you can think of HKLL. You don't have to use HKLL. You can just say write down the mode expansion. Just write down your standard mode expansion for the Bach field theory. So the Bach field is right in terms of A and A dagger. And then by definition, A and A dagger are the boundary operator. So this Bach field is just expressed in terms of the boundary operator because A and A dagger are boundary operators.
Yeah, right. Well, I mean, there is some map involved, but.
Yeah. So this A and A dagger is essentially the operator, the A dagger in the Bach quantum field theory are essentially the A and A dagger in the generalized free field on the boundary. So these are identified. And so this A dagger, they are just essentially is the A and A dagger of the boundary generalized free fields. And then so this way, whenever you write down this Bach expansion, and then I think this point was actually first point. Was known to many people. I think also Surad and Papadodimos they emphasized this point in their paper. Yeah.
But isn't there a sort of non-locality involved here? I mean, when you're doing a HKLL sort of thing, isn't there a sort of non-local dependence on the boundary for the bulk operators?
So you don't have literally do HKLL. So so essentially, the mode expansion on the gravity side, just the trivial quantum field theory mode expansion on the gravity side, that's already HKLL in the sense that express you in terms of A and A dagger, that A and A dagger is already the boundary operator. So you don't have to do more fancy this HKLL to express in terms of the local local operators on the boundary. And that procedure turned out to be not well defined for the black hole geometry.
But if you say that the creation annihilation operators match between the bulk and the boundary, what would they mean for the degrees of freedom for the fields?
No, they just identified.
But in the bulk, you have gravitational degrees of freedom, right?
Yeah, but so this is the statement that the GNS Hilbert space on the boundary is identified with the Fock space in the bulk. So this is the map of the state from the boundary to the bulk. And so you have the map of the boundaries, boundary Hilbert space to the bulk Hilbert space, then you map A and A dagger too. So they're identified. They're literally the same thing.
Yeah, the question is, what does it mean in terms of the ADS-CFT correspondence? Because in the ADS-CFT correspondence, the degrees of freedom, the A's and the A daggers can't be the same, as you are saying.
Sorry?
From the ADS-CFT correspondence point of view, the A's and the A daggers of the bulk and the boundary can't be identified in any sense.
No, they're just identified.
In what sense?
I'm not sure. They're just identified, not in what sense. They just identified they're equal.
I think Emil had the question. Can you respond to that question? Or yeah, Spencer, yeah.
Yeah, I wanted to ask about how the left and right are getting mixed. So if I understand correctly, this operator G, as you say, it somehow involves both left and right transformations. But could you say a little bit more about how the left and the right? I mean, I guess what I'm wondering is, we know in the past of, this sort of Gauge-Ferris wall construction where, if you have some operation, some operator, some bilinear operator that couples the left and the right, then, you can execute some operation that indeed takes you through the bulk.
Right.
From one, and from one side to the other.
Right.
But that's not something that's built in from the beginning, right? You just have entanglement without some sort of quantum channel that would enable you to pass information from one side to the other. So could you say a little bit more about how your operator G is accomplishing that?
So this G is just yeah, I think it's something similar to that in the sense is that the it just you have to we didn't write so to write G down explicitly in terms of your boundary degree freedom is complicated. So what we did is we went around that. We write down how the G, how this U act on this generalized free field algebra. Okay, so we actually didn't write down the G itself. We write down we write down the action of, we write down the action of G under this generalized free field algebra. It turned out that thing can be worked out explicitly. And the writing down G itself is actually a pretty complicated thing. So in the case of JT gravity, which is due to SYK, so I believe you should be able to write down this G explicitly. And so I believe the answer is, in that case, there was some earlier paper by Chi and Marcina, and also by Marcina, Henry Lin and Zhao, in Zhao, which they write down some SL2R algebra. Again, that kind of SL2R algebra involve both the left and the right operators, etc. And I think precisely in that particular context, the operator they wrote down in that context is precisely this emergent type III1 algebra. It's our G for that case. So in that case, you should be able to make it very explicit.
Yeah, the kind of thing that confuses me about this is always that it's something that seems like it's introduced by hand. So in other words, I could always evolve with the usual Hamiltonian, which doesn't couple the left and right. And then, you know, the left and right sides just don't talk to each other. So you say, okay, I'm going to use this different operator. So, and now this, you know, allows me to realize what's going on behind the horizon. But in a way where I've only accessed that by making the left and right talk to each other. So it's sort of like, it's maybe, I don't know if this is some manifestation of complementarity between the interior and the outside or something else, but it seems like it's sort of like this question about, is it there if you don't ask it to happen?
Right.
That you sort of can't recover the experience of the people who don't use that Hamiltonian and don't have any coupling between the left and right world, because you've done something to the system that explicitly couples them.
Right. So first, those are the kind of operators which exist in your theory. So even in your original theory, your time is generated just by HL and HR, but this kind of operators, they do exist in your theory. And it's a legitimate question to ask, what kind of evolution does this kind of operate these two? So they generate some kind of automorphism, say, of the algebra of your theory. And so you can ask what kind of automorphism they generate, okay? But then it turns out this kind of operations, they do corresponding to the Bach evolution. So the Bach evolution somehow have to involve this kind of operators.
Right. But if I didn't restrict myself to single trace operators, I think we all believe that ADS CFT is a duality. Yeah. And so the full operator algebra, the full theory describes everything that's going on everywhere, including inside the horizon. And so if in that description, I've not explicitly coupled the left and the right, I've just entangled them, then there's no way that, you know, throwing something in from the left can make it collide with something from the right, because there's no quantum channel that would allow them to talk to each other. So I'm confused by how to square that statements that you're making about the algebra of single trace operators with the properties of the full theory, which is supposed to describe everything if I include all the operators, you know, beyond single trace, where the left and right just aren't talking to each other.
They still talk to each other, right? Still, even when you go to the full theory, so when you go to the full theory, you can still construct such kind of operators. These operators still exist in the full theory. And just in the Largian limits, you can isolate this sub-algebra, which corresponding to the single trace operator algebra. But such operators, they exist in the full theory. Just in the full theory, when you go to finite n in the full theory, they don't generate a sharp horizon. They still have some kind of approximate notion. So if n is sufficiently large, even at finite n, you still have some approximate notion of a horizon, some interior region, etc., still generated by this kind of operator. It just depends on what you mean by describing the Bach. We will not, there's no rule telling us somehow the Bach evolution can only be described using HL and HR, or some kind of linear superposition of them. There's no rule tell us that has to be the case. HL and HR, they generate some kind of symptotic time evolution. But if you really want to think about the evolution in the interior of the space-time, there's no rule tell us we have to use HL and HR. And we know HL and HR cannot be enough. Cannot be enough to do that. Because if you want to do something inside the horizon, you have to couple the L and the right in some kind of non-trivial way.
Emil, would it satisfy you if one were to say that maybe the invariant way to ask this question is you throw an observer in from the right-hand side, and then maybe you have something else, a shock wave from the left-hand side. Afterwards, you couple the left and the right explicitly so as to pull the observer out using some Gauss-Jeffreys-Wald proposal, and then you interrogate the observer about whether they saw the shock wave or not. That would be an invariant question, and it would get rid of the objection of the concern that you had, which is that the left and right were not coupled, because now you did couple them to pull the observer out. And then maybe these questions could be framed in that way, that when we ask the question about what the observer sees as they fall in, we are trying to answer what the observer would answer if we were to pull them out by coupling the left and the right and opening up the wormhole. I mean, would that make you happier?
Yeah, it's a question about if I don't do that, if I just let the system evolve the way it wants to evolve with its own Hamiltonian, will I see any of these effects?
Yeah, so that's the question of course, yeah, what are the operators that the infalling observer uses, right? And does the infalling, I mean, the infalling observer, yeah, so if you have a shock wave from the left, does the infalling observer see the shock wave or not? So usually we would say the infalling observer would, but you're right that, the infalling observer could use some other set of operators to make the shock wave go away. And I agree. I'm not sure how to answer that question invariantly without doing something to pull the observer out. But yeah.
Okay. Since it's pretty late, we should probably conclude our seminar now. Let's thank Professor Hong Liu for a really wonderful talk.
Okay, thank you. Yeah,
Thank you, Hong.
thanks. Yeah.
Thanks, Hong. Thank you.
Okay.
My God, you must be very sleepy by now.
Yes.
Okay, good. Yeah. Thanks for coming and all the questions. Yeah.
Thank you.
Thank you. Bye-bye.
Okay, bye. Yeah. Bye.